Hi friend, welcome all to my educational channel Math A to Z. Today's topic is cyclic group. Here we first give the definition of cyclic group and the properties of cyclic group one by one. Some property we discuss in this class and another some property we discuss in the next video. So we come to the definition of cyclic group. Definition. A group G or G circle is said to a cyclic group if there exists an element A belongs to G. There exists an element A belongs to G such that G can be written as G is equal to A to the power n, where n belongs to set of integer. And here we mean A to the power n is equal to A circle to A n times. If we consider the operation circle like as addition, then this definition or this group may be written as G is equal to NA such that n belongs to Z, right? That is, here NA is equal to A plus 2A n times, and this is the definition of cyclic group. Here we consider the operation like as multiplication, and here we consider the operation like as addition. Now we go to the example of cyclic group. We first consider a very easy example. We consider the set of cube root of unity, and we all know it has three elements, 1 omega square. Now if we generate 1, then we get only 1. But if we generate omega, then we get first element as omega, because omega to the power 1, second element omega to the power 2, and the last element, that is omega cube, this is equal to 1. So we get the whole group or whole set S. Similarly, if we generate omega square, then we get omega square, omega to the power 4, that is, we know that it is omega, and omega to the power 6, this is 1, and this is also S. So we can say here this group is a cyclic group, and it is written as generated by omega or generated by omega square. And here we say that this group G, which is cyclic, can be written also as A, and the element A which generates the group is called generator of the cyclic group. Generator of the cyclic group, right? So here we get two generators of this cyclic group. Now if we consider the group, another important group V, that is Kelvin's 4 group. which is E, A, B and C, and we know its all property. Here if we generate E, then we only get the element identity E. If we generate A, and this get E and A, because first element is A and second element is A square, and this is E, because from the property of Kelm's-Porter group. Similarly, if we generate B, then we get B and E, and if we generate C, then we get C and E. So there is no element such that which can be generate V. So we say that V is not a cyclic group, not a cyclic. Right? Similarly, if we consider another important example, we consider the nth root of unity. Nth root of unity, which is given by cos 2k plus 2 into k plus 1 by n plus I sine 2 into k plus 1 by n. This is the value of x, which is the nth root of unity, where k is equal to 0, 1, 2 to n minus 1. If we take k equal to 0, then we get the value of x, and we name this as x0. This is cos of 2, here is a pi and also here is a pi, 2 pi by n plus I sine 2 pi by n. And clearly this element can generate the whole group, that is all the n elements of this group, x0, x1, x2 to xn minus 1. So this is also a cyclic group, right? And if we take the group like this Zn with respect to addition module again, here also a cyclic group, because this group can be generated by the element 1, because we know that if we generate 1, then we get first element is 1 plus, second is 2 plus, third is 3 plus, to n minus 1 plus to n plus, that is 0 plus, and here this is the last element. So we get all the element of Zn by generating 1 plus, and this is also a cyclic group, right? So this is the definition, and these are the example, or we also say important example of cyclic group. Now we go to the first property, or we say that the first theorem on cyclic group. First theorem is let G circle be a cyclic group and A be the generator. A be the generator. Then A inverse is also generator of G, right? That is, if A be the generator, then the inverse of A is also the generator of G. Now here it is given that G is equal to this, and this is written as a to the power n such that n belongs to Z, and we have to prove that G is also can be written as that type. Now to prove this, we first let H be a set such that which generate a to the power minus 1, that is the inverse of A. Now we first let any element from G. Let P be the element of G. Since G generated by A, so the form of P must be a to the power m, where m is an integer, right? And we can write P as a to the power minus 1 whole to the power minus m. And since m belongs to Z, obviously minus m is also belongs to Z. So we can say that this element, that is P, is also belongs to H, because this type element is here. So we can write P belongs to H. Now we start from this P belongs to G and we prove this P belongs to H. So from this to this we get G is a subset of H. Also, on the other side, if we take an element Q belongs to H, then this element must be of the form a to the power minus 1 to the power s. Okay, and also, here s belongs to Z. And this is also written as a to the power minus s, where minus s belongs to Z. So this form is like that, a to the power n, because n belongs to Z. Here a to the power minus n, minus s belongs to Z. So we say that Q must be belongs to G. Now here start from Q belongs to H and we arrived at Q belongs to G. So we can write H is a subset of G. So from this and this we say that G and H are both equal. And since H is like that, that is cyclic group generated by a to the power minus 1. So G and H are equal means G is generated by a to the power minus 1. So if we find one generator of the group, then we can also write the inverse of this generator is also generate this group. Okay. Now we go to the second property or second example of the group or second theorem of the group, theorem 2. Every cyclic group is commutative. This is very easy property or very easy theorem. We take first a cyclic group generated by A, that is a to the power n such that n belongs to Z. This is the cyclic group. Now we take any two element P and Q. So P is of the form a to the power r and Q is of the form a to the power s. Now P into Q or P composition Q is equal to a to the power r composition a to the power s. This is a to the power r plus s and this is a to the power s plus r. S plus r, and this is a to the power s composition a to the power r. This is Q composition P. So clearly PQ is equal to QP for all PQ belongs to G. So G circle must be abelian or commutative. But converse of this theorem may not true, because if we take one important example again, Kelvin's 4 group. Kelvin's 4 group. We know that this is abelian, but we already proved here in this class this is not cyclic. Okay, but some important example here by using this property. If we take the group S3, that is the permutation group of 3 symbol, and we know that S3 is non-commutative. Also, if we take dihedral group Dn, okay, then for this also these are non-commutative group, and from this theorem we say that since these group are non-commutative, so these are must not be cyclic, because if these are cyclic then it must be commutative, but commutative is not cyclic. But here these group are not commutative, so it cannot be cyclic group. So we say that this group and this group are not cyclic. Now go to the last property of the class or last theorem of the class. Here let G circle be a finite group and G is generated by A, and since it is finite group, so order of G must be finite, let it be n, and this is implies and implied by order of A is equal to n. So we say that the order of cyclic group must be equal to the order of the generator of this cyclic group. Now we go to the first part. Here we take order of A is equal to n, and since order of A is equal to n, then we must have A square, A cube to A to the power n. This is E. These are all distinct elements. Since if these are all not distinct, then we let A to the power R and A to the power S are 2 elements of this list. These are same, where R greater than S, but this is less equal to n and this is greater equal to 1. And from this relation we say that A to the power R minus S is equal to E. So order of A less equal to R minus S. But since R and S lies between 1 and n, so this must be less than n. But this contradicts our assumption, because we here assume order of A is equal to n. So these elements are must distinct element of this list. Now since A be the generator, so A must be belongs to the group, and by closure property, if A belongs to G, so all the power of A, that is A square, A cube, also A to the power minus 2, A to the power minus 3, A to the power minus 1, all the power of A must be belongs to G. So if we take this as a set, then this is the subset of G. Now if we prove, or if we can prove G is a subset of this set, G is a subset of this set, then we can write this is equal to this, and here G is given by a cyclic group generated by A. So we can write G is equal to A to the power n such that n belongs to Z. Now we take any element P belongs to G such that P is equal to A to the power n. And by division algorithm we can write M is equal to NQ plus R, where Q be the quotient and R be the remainder. Here both Q, R must be belongs to Z and 0 less equal to R less than N. Because if we divide M by N, then the remainder must be less than N. And if the remainder be 0, then this is 0 less equal to R and less than N. Now P can be written as A to the power M and this is A to the power NQ plus R. So A to the power N whole to the power Q composition A to the power R and this is E. So this is A to the power R. And since R is lies between 0 and N, so we say that A to the power R must be in this set, because here all power of A to the power 1, A to the power 2 to A to the power n are lies here. So we say that P belongs to this set, A square to A to the power n. And since we take first P belongs to G and we prove P belongs to this set, so we can write this. That is, we say that G is equal to this set. And since these are the distinct n element and G is equal to this set, so we clearly say that G contains n elements only. That is, order of G is equal to n. So we first take order of A equal to n, then we prove order of G is also equal to n. Now we try to prove the only if part. That is, here we take order of G is equal to n and we try to find order of A is equal to n. Right? Now, since order of G is equal to n and n is finite, so for all A belongs to G, we know that order of A less equal to order of G is equal to K and this is less equal to n. If K is less than n, strictly less than n, then from the first part we already proved if order of A is equal to n, then order of G is equal to n. This can prove already. Now if we take order of A is K, which is less than n, then order of G is also K must. But our assumption is order of J is equal to n. So from the first part or by using the first part, we say that order of A is equal to K less equal to n. This hold only K is equal to n. Okay, so we take order of G is equal to n, then order of A must be equal to n. And similarly, this theorem can also be stated for the infinite group. If G circle be infinite group and G is generated by A, then order of G and order of A must be infinite. This is infinite. Here it is given that this is infinite, so this is also infinite. And it is shown very easily if we take this is infinite. order of A is infinite. Then A square, A cube to this. This is the infinite distinct element of G. Because if these are not distinct, infinitely distinct element, if sum two are equal, let a to the power r is equal to a to the power s. Then in previous manner we say that order of A must be finite. But this is not so, because it is given that this is infinite. So this element must belongs to, or this set must a subset of the group G. And there is infinite number of elements. So the mother set or the superset must be infinite number of elements. So we write that this implies order of G is also infinite. Okay, and conversely we say that if order of G is infinite and if possible order of A is finite, here is also a contradiction, because if order of A is finite, then we already proved on the previous theorem order of G must be finite, because G is a cyclic group generated by A. But our assumption is order of G is infinite. So if order of G is infinite, then must be order of A is infinite. Okay, so order of G and order of A must be infinite here together. Okay, so friend, this is the today's class. Thank you for watching.